Good evening and welcome back to the sleep journey. Right now, there is an opening in the sun's outer atmosphere, not as a metaphor, a real, measurable region in the corona, darker, thinner, and vast. It's been described as enormous, so large you could compare it to dozens of Earths side by side. And from that opening, a stream of solar wind is flowing outward, fast, around 800 kilometers per second. Some scientists have given it a dramatic nickname, Goliath, and if you know what coronal holes can do, that name can feel heavy. But what makes this moment feel different isn't only the sun, it's us. Because Earth isn't supposed to be fragile right now, our magnetic field, the invisible shield around the planet, should be doing its job. And it is, mostly, but it hasn't been as strong as it used to be. For decades, measurements have suggested it's slowly changing. One well-known weak region, the South Atlantic anomaly, has been spreading. Some studies also suggest changes deep in Earth's core, subtle shifts in motion over time. And then just days before this solar opening became so pronounced, an interstellar object passed through our neighborhood, close enough to capture attention. And soon after, instruments on Earth reported something strange low. Unusual vibrations, not quite like ordinary earthquakes. Is that a coincidence? It might be. Or it could be something else, not separate events, but a sequence. Tonight, we're going to move slowly and carefully. We'll look at what's confirmed, what's uncertain, and what's simply worth watching. Stay with me to the end, because some patterns don't wait for us to name them. And if you want to keep following this trail as new evidence appears, you can subscribe. And for a moment, tell me where you're listening from, your time zone, and whether you feel the mainstream explanation captures the whole story or only part of it. Part 1. The moment we looked away, we were watching the wrong thing. On December 19th, 2024, telescopes around the world tracked an interstellar visitor called 3I, Atlas. It moved through the solar system at roughly 47 kilometers per second. News outlets followed its approach. Researchers discussed what it might be made of. And amateur astronomers shared images soft, grainy, and mesmerizing. A piece of material traveling between stars long before human history began. For a while, everyone was looking up. And while we watched, something else may have been unfolding, quietly, close to home. Within about 48 hours of the flyby, seismometers across the western United States began recording unusual signatures, not classic earthquakes, something stranger. A low-frequency humming, like the crust was vibrating, at notes it doesn't usually hold. Fault zones from California to Alaska showed subtle stress anomalies. The Pacific Ring of Fire, always restless, seemed a little more awake. And then, as if answering a cue we couldn't hear, the sun did something uncommon. A massive coronal hole opened. And not just any hole. The kind that makes solar physicists pause mid-sentence and stare. Again, that nickname Goliath. Because it isn't only about size, it's about timing. It's about sequence. It's about what happens when a system already under strain gets tested. Here's what we can say with confidence, without fear, without guessing. The interstellar object reached closest approach on December 19th. Seismic networks recorded real anomalies in the days that followed, and satellites confirmed a large coronal hole, oriented in a way that sends its outflow toward Earth. Geomagnetic measurements also show disturbances consistent with incoming solar wind. These are documented observations across independent systems. What remains uncertain is the connection, whether these events are linked, and what it would mean, if they are, for a planet whose magnetic shield has been quietly changing for a long time. We often imagine Earth as either protected or not, like a switch, but the magnetosphere doesn't work that way. It's a dynamic boundary, always flexing. It compresses under pressure and expands when conditions ease. It has thin spots and leak points where particles can slip through more easily. And in late December of 2024, Earth's shield wasn't at full strength. Not gone. Not failing. Just less robust than we like to believe. Measurements suggest the magnetic field has weakened gradually over centuries, with a noticeable decline over the last couple of hundred years. We've known this, and we've watched it, but we treat it like a slow problem, a future generation problem. What if the timeline is faster than we assumed? What if Earth isn't a passive target, but a stress system, already carrying weight close to its limit, because that changes how we interpret everything. A fast solar wind stream becomes more than routine space weather. It becomes a pressure test of a shield that may already be tired. And the sun, all year, has been unusually active. Solar cycle 25 has produced stronger activity than many forecasts expected. Large flares, eruptions, and now this enormous opening in the corona releasing fast plasma, like a steady current. In public, forecasters remain calm. Coronal holes are normal, they say. And that's true, sometimes they are. But in quieter spaces, research meetings, conferences, some admit they didn't expect this particular combination, not this size, not this alignment, not this timing. There's a phrase you may hear whispered in the space weather community: energetic sequencing, the idea that events don't arrive alone, they can arrive in cascades. One disturbance sets the stage for the next. And timing can matter more than sheer force. A fault system already stressed may respond to a tiny extra push. A magnetosphere already compressed may absorb less of the next wave. A system near threshold does. It need a huge udar, just the right pressure at the right moment. Like tapping a cracked windshield, exactly where the fracture lines meet. And then comes the uncomfortable thought, not that the sun decides anything, but that complex plasma systems can respond to disturbance. Ripples propagate, pressure moves through connected fields. Could an interstellar object, passing through magnetic structures, have altered anything? It sounds like science fiction. And maybe it is. Maybe it's coincidence. Maybe the coronal hole would have formed anyway, and the visitor was simply passing through a neighborhood already changing. But the timeline feels tight. The sequence feels clean. And the consequences, if the pattern continues, are real. Because right now, a stream of high-speed particles is moving toward Earth, around 800 kilometers per second. It will arrive soon. And when it does, it won't meet a perfectly rested shield. It will meet a magnetosphere that may already be under load. Part 2. Why the Goliath hole doesn't feel normal. Solar physicists have a talent for making dramatic things sound ordinary. They can describe a vast missing region in the corona, where magnetic lines open outward and a river of superheated particles escapes, and still call it a feature of interest. But this isn't one of those moments. This is the moment where words get careful, where unusual configuration means we're paying close attention. Coronal holes do happen. Let's say that clearly. The sun's corona often develops regions where magnetic field lines open outward instead of looping back down, and plasma follows those open lines, streaming into space as fast solar wind. In extreme ultraviolet images, these regions look darker, cooler, and less dense than the surroundings. They're like vents. Usually, they appear near the poles. Usually, they're broken up, fragmented. Usually, they shift and dissolve over days. This one is different. Major solar observatories captured it, forming over several days in mid to late December. It stretches from high northern latitudes down toward the equator, an elongated opening across a large portion of the visible solar disk. That geometry is unusual near solar maximum. At this phase, we expect the corona to look chaotic, small structures, scattered and messy. Not a coherent, a stable feature that looks organized. And then there's the orientation. Its magnetic configuration aims the outflow almost directly along the Sun-Earth line. Imagine a garden hose. Now imagine it's unimaginably wide, and the spray is ionized particles moving at extraordinary speed. Many coronal hole streams miss Earth. They angle away or sweep past as the sun rotates. This one lines up, not by intention, not as a choice, just as a consequence of how the sun's magnetic field opened. Right here, right now, official warnings were issued in standard language. Possible minor geomagnetic storms, auroras at higher latitudes, potential effects on satellites. But inside the technical wording are clues: extended duration, elevated background levels, multiple arrival phases, meaning this may not be a quick hit. It may be sustained pressure. Some researchers suggest features like this can persist for weeks, rotating with the sun, sending repeated fast streams toward the same targets. And in studies of historic extreme events, there's evidence Earth is sometimes affected not by one blow, but by a sequence arriving while the magnetosphere is still recovering. The mainstream explanation remains calm. Solar maximum is active. This happens. We're prepared. And it might be right. But quietly, another question lingers. Why this shape? Now, why so coherent when everything should be messy? It's not breaking the laws of solar physics. It's simply operating close to the edge of what observers expect. Like watching someone balance too steadily and realizing you don't know what they know. And there's one more detailed polarity. The field lines inside the opening show a dominant direction, as expected, but nearby structures also appear more organized than usual, as if the formation nudged the surroundings into alignment. It resembles a system finding an efficient way to release pressure. The sun doesn't think, but physics can settle into patterns that look uncomfortably purposeful. So here we are, a massive, stable, well-aligned coronal hole sending fast solar wind toward Earth. In a few days, that flow reaches our planet, and it won't be arriving to a pristine shield. It will be arriving to a system that may already be stretched, already humming, already using some of its margin for error. You can call the timing coincidence only so many times before coincidence begins to look like a pattern. And, in complex systems, patterns often appear right before a shift. Part 3. Earth wasn't starting from zero. Picture a quiet rain outside your window. Now picture holding a coat that has lasted a long time. Still usable, still protective, but the seams have thinned in places you don't notice until the weather turns rough. That's closer to what Earth's magnetic shielding is like right now. Not gone, not collapsing, just uneven and increasingly measurable. The magnetic shield isn't a hard shell. It's a moving boundary made of fields and charged particles. It shifts with every change in solar wind. It expands, it compresses, it flexes, and it relaxes. And that motion depends on two things at once: the conditions in space around us and the deep magnetic engine inside Earth itself. Earth's field is generated by motion in the molten outer core, a slow churn of conductive metal that acts like a dynamo. It's been running for billions of years, shaping a protective bubble that helps keep our atmosphere stable and helps reduce the radiation that would otherwise reach the surface. But the field isn't perfectly steady. It drifts. It strengthens and weakens over long spans of time. And in the current era, the trend has been a gradual decline, not sudden, not dramatic, but persistent. One region in particular has drawn attention for years: the South Atlantic anomaly, a broad area where the magnetic field is weaker than expected. Satellites passing through that zone often experience more radiation impacts, more glitches, more small errors that engineers have learned to anticipate. The shield still works, but it has thin zones, and those thin zones can widen. Space weather events are rated from G1 to G5. A mild storm might bring brighter auroras and small disturbances to high-latitude power systems. A severe storm rare, but possible, can create serious stress on grids, disrupt radio communication, and interfere with satellite operations. We've seen impactful events before: storms that caused outages, equipment damage, and satellite anomalies. What we haven't experienced, at least not in the modern technological age, is a true extreme Carrington-level scenario, and that's part of the tension. Not panic, just a quiet awareness, because not recently doesn't mean never, and luck isn't the same thing as readiness. In the days leading into this late December period, Earth's magnetic environment wasn't perfectly calm. Monitoring stations observed elevated background activity, not a full storm, more like sustained turbulence. Solar wind conditions had been shifting speed, density, and magnetic orientation changing enough to keep the magnetosphere somewhat compressed. Not an emergency, but not ideal conditions either. Ground magnetometers recorded fluctuations. Auroras showed up a little farther from the poles than usual. Nothing headline-worthy, just the kind of subtle noise that says the system is already carrying extra load. And when a system is already loaded, even ordinary stress can feel louder. One important detail is this: the magnetosphere doesn't respond evenly across the whole planet. When solar wind pressure increases, the day side facing the sun compresses. The night side stretches into a long magnetic tail. Particles can enter through polar regions, through transient cracks and reconnection events, and through turbulent mixing zones where different plasma populations meet. That means there can be localized weak regions, temporary, shifting places where incoming energy couples more efficiently into the system. And one of the regions some researchers watch closely sits over western North America, near highly monitored fault systems, including California's major tectonic boundaries. California matters for another reason too. Its geology is complex and conductive in places with saltwater aquifers, mineral-rich layers, and interconnected faults. Think of it as a landscape that can guide electrical currents in complicated ways. When geomagnetic conditions intensify, currents can be induced in the ground, often called geomagnetically induced currents. They follow paths of least resistance through conductive rock and water. They can also couple into long conductors. We build power lines, pipelines, creating engineering challenges that grid operators take seriously. Now, there's a delicate point here. The idea that electromagnetic disturbances can influence earthquakes is not a mainstream conclusion. Most geologists will rightly emphasize earthquakes happen because plates move. Stress accumulates, and rock fails. That's the foundation, and it doesn't change. But there's also a well-known nuance. Faults already close to failure can be triggered by very small additional stresses. We've seen correlations with reservoir filling, groundwater changes, even tides in certain conditions. So the question becomes quiet and specific. Could geomagnetic disturbances ever act as a small triggering factor when everything is already lined up? The cautious answer is maybe sometimes under the right combination of factors in certain places at certain moments. Not causation in the dramatic sense, more like a final nudge, a last grain of sand effect. Studies looking for links between solar activity and seismic timing have produced mixed results. And mixed results are exactly what you'd expect if the relationship, if it exists at all, is weak, conditional, and easy to bury under normal geological noise. Some analyses find patterns, others don't. Some only find effects during certain phases of the solar cycle or in specific types of tectonic settings. That's what subtle triggering looks like. Not a single clear cause, not a simple chain, just a possibility that the final step happens more easily when multiple pressures overlap. In the western United States, seismic monitoring is incredibly dense. Microquakes, tiny strange shifts, small swarms, things no one feels are still recorded and catalogued. And in the days following that interstellar flyby, some instruments reported activity that didn't match the usual baseline perfectly, clusters of small events in unexpected spots, shifts in strain patterns near major faults. Again, nothing that demanded alarms, nothing that forced anyone to run, just anomalies. The kind scientists note, and then compare, and then watch. And then the magnetic data showed something else, something that, in this telling, felt out of place. Patterns at specific frequencies appeared resonant structures that are usually faint. Frequencies associated with natural oscillations in Earth's near-space environment, ultra-low frequency pulsations, and resonance modes in the coupled system of the magnetosphere and ionosphere. These signals can exist quietly in the background, but what stood out was their clarity, their persistence during a time when conditions were expected to be too messy for clean ringing. It's like hearing a pure tone in the middle of wind and rain. Not impossible, just unusual. And sometimes, systems under stress don't fail by snapping. Sometimes they reveal strain by resonating, by holding a note longer than expected. In late December, the planet seemed, at least in these measurements, to be sustaining tones that didn't quite match the moment. And that brings us to the next part, Part 4, Resonance over California. Everything that can move can vibrate, and everything that vibrates has preferred frequencies, notes it naturally returns to when disturbed. A guitar string, a glass bottle, a bell, each has its own resonant signature. Earth does too. The space between Earth's surface and the ionosphere forms a kind of cavity, a region where electromagnetic waves can bounce and form standing patterns. The magnetosphere itself can oscillate as well, flexing under pressure like a stretched membrane. These aren't metaphors. They're measurable phenomena, studied and recorded by space physicists and geophysicists. What's not routine is seeing strong resonance patterns during a period when geomagnetic conditions should be too disturbed to allow clean, coherent ringing. Schumann resonances, one well-known set of global resonance modes, were predicted in the early 1950 seconds by physicist Winfried Otto Schumann, and confirmed experimentally soon after. And in this story, those quiet planetary notes seem to rise into view, clearer than expected, right when the environment should have been too noisy to hold them. Schumann resonances are extremely low-frequency electromagnetic waves. The fundamental mode sits around 783 Hz, with other harmonics above it. They're continually excited by lightning storms striking around the globe, over and over feeding energy into the space between Earth's surface and the ionosphere, like a slow, invisible drumbeat. These resonances are basically always present, a quiet background tone in the planet's electromagnetic environment. And they drift a little with seasons, with solar conditions, and with where thunderstorms are most active. Some researchers have wondered whether they might interact with biological systems. That idea remains debated, and far from settled. What is settled is something simpler to measure Schumann resonances clearly. You usually want calm conditions. When space weather gets rough, when solar wind stirs the magnetosphere, the delicate resonance patterns tend to get buried under the noise. But this time, they weren't. In late December, magnetometer networks reported clean, strong resonance patterns, even while geomagnetic indicators suggested the environment was still unsettled. Stations in California saw it clearly. So did instruments in Alaska. So did high-latitude monitors in Scandinavia. The signal looked global, but not evenly spread. The strongest detections tended to appear in regions where Earth's magnetic field lines connect more directly to the magnetosphere's active outer boundary places that feel space weather more immediately. And alongside those Schumann signatures, instruments also picked up ultra-low frequency pulsations, oscillations of the magnetosphere itself, with periods from seconds to minutes. These are not the same thing as Schumann resonances. ULF pulsations are driven by how the solar wind presses on Earth's magnetic bubble by pressure surges, wave modes, and interactions along the magnetosphere's edge. The technical description for what observers were seeing was something like spectral coherence during active conditions. In plain language, patterns that normally show up during quiet were appearing during disturbance. Imagine trying to hear a single clear note while a whole room is full of competing sounds, or watching a pond's surface form a neat, repeating pattern even as raindrops keep hitting it from every direction. Physics doesn't forbid it, but it suggests the system is in a very specific setup, one that may be telling you something. Naturally, skeptics pointed to the simplest explanation. First, instrument problems. Magnetometers can misbehave. Data filters can accidentally create shapes that look meaningful, and one station can be fooled. But when many stations separated by great distances, using different hardware report the same kind of feature, pure artifact becomes harder to argue, though still not impossible. Teams checked. Solar observatories reviewed equipment. Universities ran diagnostics on their arrays. Commercial space weather services cross-validated the feeds, and the signals remained. They appeared consistent. They appeared persistent. They appeared real. So, the question shifted from, is it there, to what does it mean? One interpretation, the cautious one, says this is a curious, non-alarming anomaly. The magnetosphere is complicated. It can support resonant modes, even when it's being disturbed. If the geometry and boundary conditions line up just right, maybe the incoming solar wind had a configuration that happened to enhance certain frequencies. Maybe compression and shape changes in the magnetosphere created an unexpected amplifier. And maybe it's simply a reminder that we still don't fully understand how Earth's magnetic environment responds moment to moment. That's a reasonable view, and it may be the correct one. But there's another angle to consider quietly, carefully. Resonance isn't just motion. Resonance is gain. If you nudge a system at the frequency it naturally prefers, the response can build not because the push is strong, but because the timing is perfect. That's the principle behind small forces producing big effects. It's why a steady rhythm can make a structure sway more than expected. Why repeated timing can matter more than raw strength. So if Earth's magnetosphere was resonating while solar wind energy arrived, it could mean the disturbance wasn't merely hitting Earth, it was coupling in, and, in certain modes, being strengthened. Now, gently connect that to what was happening underfoot. Seismologists already know something important. Rock under stress can be sensitive to tiny periodic forces. Tidal effects, the subtle pull of the moon and the sun, are weak compared to tectonic forces. Yet some studies find small correlations between tides and earthquake timing in certain settings. The effect is modest, but it suggests a real principle: faults near failure can be tipped sooner, by small external nudges. So here's a possible mechanism spoken cautiously. If geomagnetic disturbances induce currents in the crust, and if those currents pulse in ways that couple to conductive layers, fluids, or fractured zones, then electromagnetic activity might under narrow conditions influence timing, not create earthquakes from nothing, not shatter the ground, just shift the moment a failure happens that was already on its way. This is highly speculative. Most seismologists would not endorse it as established. Evidence remains mixed and contested, but speculative ideas become more interesting when multiple separate observations seem to lean the same direction. An interstellar flyby, followed by odd seismic signatures. A major coronal hole, followed by unusual resonance behavior. California showing both electromagnetic patterns and seismic anomalies in the same window. Any one piece could be chance. Altogether, it begins to look either like an elaborate coincidence or a pattern we're not skilled at recognizing yet. A metaphor some researchers use carefully, often informally, is that Earth behaved like a struck instrument, not breaking, not failing, just ringing. The sun provided an input. The magnetosphere shaped it. The crust may have registered it. And somewhere in that chain, a stressed fault system might have been nudged a fraction closer to the threshold it was already approaching. Resonance is quiet. It doesn't arrive with fireworks. It accumulates. It stores energy in repeating motion, sometimes persisting after the initial push is gone. So if Earth was truly ringing in late December, a calm question follows. What happens when the next push arrives? When the fast solar wind stream from that huge coronal opening reaches a planet that's already humming? Does the response grow? Does it amplify? Does it feed back into itself? Or does it all dissolve into the usual background complexity? Another noisy dataset. Another argument about weak correlations. Another mystery that never resolves cleanly. The uneasy part is that we don't get certainty ahead of time. We only learn after the system has responded. And in this storyline, the solar wind is already on its way. Earth is already active. And California, positioned under a region some consider magnetically vulnerable, is simply waiting. Part 5. The 1 to 2 punch hypothesis. What comes next is hypothesis, not settled fact. And it matters to say that out loud. Science moves forward by proposing explanations, testing them, and letting most of them fail. Patterns often collapse under better data. Mechanisms that sound plausible can disappear under measurement. That's normal. That's healthy. But sometimes a hypothesis survives, refines, and earns its place. So here is a careful idea offered to be tested and discarded if wrong. What if Earth wasn't dealing with independent stresses, but a sequence where the order mattered as much as the strength? Start with the interstellar visitor, 3I, Atlas, possibly a large object, perhaps on the order of kilometers across, moving through the inner solar system around 47 kilometers per second. That speed isn't extraordinary on cosmic scales, but it's enough to matter in a plasma environment, because objects like comets are not electrically quiet. As sunlight warms them, gas can stream off, become ionized, form plasma, and interact with the solar wind. That interaction can create bow shocks and magnetic disturbances, effects that, in some cases, can extend enormous distances. In other words, a passing body can leave a kind of wake in the solar wind's electromagnetic structure. It can perturb field lines. It can generate pressure ripples in surrounding plasma, and those ripples can spread. Whether any planet feels something from that depends on timing, geometry, and magnitude. Gravitationally, a flyby like this almost certainly wouldn't tug Earth in any measurable tidal way too small, too far, but electromagnetically, the question is different. If the object carried charge, or generated a strong enough plasma interaction, it could, in principle, to contribute a small pulse, a ripple moving through magnetic structures. Earth sits inside, not a giant pulse, not a world-cracking force, but possibly enough to slightly shift currents in conductive layers, and slightly alter timing in a system already stressed. Again, speculative. No one has confirmed strong electromagnetic signatures from 3I, Atlas. No spacecraft flew close enough to sample its plasma environment. We mainly have telescope observations trajectory, brightness, spectra, composition clues, And electromagnetic interactions in space are difficult to measure from far away. The most convincing data would be in situ spacecraft passing through the disturbed region. We don't have that. So this portion remains unproven, yet not physically impossible. Now add the Sun. A few days after the flyby, on the order of 4 days, the large coronal hole becomes prominent. 4 days is not a simple reaction time in any intentional sense. And it's not evidence that the Sun noticed anything. Solar dynamics don't work like a mind. So either the timing is coincidence, or the link, if any, is subtler. For example, what if the coronal hole was already close to forming, and small changes in surrounding plasma conditions shifted the timing or the shape? This is the kind of idea most solar physicists treat with skepticism, and rightly so. But complex systems can be sensitive. Small differences can change when something happens, even if the event was going to happen anyway. Think of a slope of snow waiting to slide. The avalanche doesn't require a boulder. Sometimes it's triggered by something much smaller, at the exact wrong moment. So the 1 to 2 punch hypothesis suggests, first, a subtle priming event not damaging on its own, but shifting stress distributions, nudging resonant conditions, reducing margin. Then a second event arrives, a sustained solar wind push coupling into a magnetosphere already unsettled, into a planet already ringing, into fault systems already close to their limits. Alone, neither event would do much. Together, the sequence might produce effects that neither could produce by itself. This is how fatigue works in materials, not one dramatic strike, but repeated smaller stresses that create tiny defects, gradually lowering tolerance. Then what looks like a moderate force becomes enough. And yes, there are strong counter-arguments. Earthquakes happen constantly without interstellar visitors. Coronal holes appear regularly, without any exotic trigger. People have searched for space weather links to seismic activity for decades without finding clean, reproducible relationships. And the human mind is built to connect dots even when dots are random. All of that is true. And it's exactly why skepticism is necessary. But skepticism doesn't mean ignoring aligned observations. It means holding them gently, testing them, and asking better questions. Earth isn't a simple billiard ball. It's a layered, interconnected system, non-linear, full of feedback, thresholds, and hidden couplings. The crust, the core, the magnetic field, the ionosphere. The magnetosphere, they influence each other in complicated ways. If we want to understand what happens when the system is perturbed, we may need to study sequences, not just isolated events. We may need to ask what happens when multiple weak forces overlap, instead of assuming weak means irrelevant. So the hypothesis, in its simplest form, is this 3I. Atlas may have softened the system quietly, subtly, if at all. Then the Sun delivered a sustained push to a magnetosphere already active, and California, sitting on stressed faults and beneath a potentially vulnerable configuration, registered the combination first. It might be wrong. It's probably wrong. But if it isn't, then the real test still lies ahead. Because the fast stream from that enormous coronal opening is still traveling, and if the idea has any validity at all, Earth is about to learn how much margin it really has. And one more detail makes this feel even stranger for some observers. This may not be only about Earth. There's a larger geometry in the solar system, an alignment cycle that comes around every couple of decades. And the date some people point to is January 6th, 2025, because that's when the spatial arrangement becomes particularly interesting. Part 6. Did the Sun react to the intruder? Let's approach a concept that can sound absurd until you picture how the heliosphere actually works. The Sun sits inside an enormous magnetic bubble called the heliosphere, extending outward for well over 100 astronomical units, a vast domain filled with flowing solar wind, carrying the Sun's magnetic field with it. Planets orbit inside this moving structure. Comets pass through it, and anything with charge or plasma around it interacts with it. The heliosphere isn't empty. It's not a clean, silent vacuum. It's plasma, a slow, flowing mix of charged particles and tangled magnetic fields. More like a living ocean than empty space. And when you disturb an ocean, you get waves. So when 3I, Atlas, moved through the inner solar system, it wasn't gliding through nothing. It was moving through a medium dynamic, electrical, responsive. We've seen this with comets we've studied up close. When a comet approaches the Sun, it often forms a small bubble of interaction, a localized environment where its gas and plasma meet the solar wind. Spacecraft have measured these encounters directly. They've observed bow shocks, places where the solar wind slows and compresses as it flows around the comet. They've also recorded magnetic field shifts, plasma instabilities, and wave patterns traveling both ahead of the comet and behind it. These aren't fringe ideas. They're standard space plasma physics. Quiet, well-established, and measurable. So when a large body cuts through the heliosphere at high speed, it can leave a wake. And wakes, travel, field lines stretched around the object can relax again. Pressure pulses can spread outward. And if at the same time the Sun's corona is already strained, already close to reorganizing, then a disturbance arriving through the surrounding plasma could, in principle, influence timing, not create the event, not control it, just tilt the moment it happens. Like nudging a stone that's already balanced at the edge. You didn't build the cliff. You didn't store the energy. You just changed when it released. And yes, many solar physicists dislike this framing, because it can sound like you're giving the Sun intention, but the Sun doesn't intend. It doesn't choose. It doesn't react emotionally. It's plasma, governed by magnetohydrodynamics and nuclear fusion. And complex systems don't need intention to look like they're responding. A sand pile doesn't decide to avalanche. It simply shifts, grain by grain, until a threshold is crossed, and then it reorganizes suddenly. And the Sun is far more complex than a sand pile with fields twisting, reconnecting, and flows that can amplify small disturbances into larger reshaping events. So the question isn't, does the Sun have agency? The question is, simpler, was the disturbance big enough to matter? And the honest answer is, we don't know. We don't have direct measurements of how 3I, Atlas altered local plasma conditions. We don't have models that can reliably trace a subtle heliospheric disturbance all the way into the corona with confidence. The physics is difficult. The scales are enormous. Still, there are hints in the wider conversation. Some studies have explored whether solar eclipses correspond with small coronal changes, though mechanisms and interpretations remain debated. Others have asked whether planetary motions, especially massive bodies like Jupiter, might coincide with certain solar behaviors, again with evidence that's suggestive but not conclusive. There are even proposals about the Sun's relationship to the broader galactic magnetic environment ideas that remain hard to test. These are not mainstream conclusions, not because they're automatically impossible, but because they're difficult to measure in clean, decisive ways. What is clear is this: in mid-December, the corona was active, fields were tangled, regions were erupting, conditions were ready for change. And within days of the interstellar flyby, a large reconfiguration appeared. The Goliath opening became obvious. Maybe that was always going to happen. Maybe it's pure coincidence. Or maybe, just maybe, the timing shifted by hours or days, and that difference mattered because Earth was in a sensitive window right then. Coincidence can stack, and stacked coincidence begins to feel like something else. When multiple unlikely timings line up, you start to wonder if a connecting thread exists that we simply haven't learned how to see. Scientists have a phrase for that moment when they won't claim a link, but also won't dismiss what they're seeing. They say more research is needed. It's a careful statement. A hedge. A way of saying something here deserves attention, but we can't name it yet. And that's where the question stands: did the Sun's timing shift? Even slightly. In response to a passing disturbance, we don't have proof. And the universe doesn't pause while we build proof. Events unfold whether we understand them or not. Patterns emerge whether we recognize them or not. Consider what it would imply if even a small timing influence were real. It would suggest the heliosphere is more interconnected than we assume, that planets aren't isolated targets in empty space, waiting for random hits. It would mean we're inside a system, a web of fields and flows where disturbances in one region might shape conditions somewhere else. That would change how we think about space weather. It would change how we estimate risk. It would change what we choose to monitor. Because if sequence and timing matter not only magnitude, then our models may be missing an important dimension. And that leads to an analogy that makes some people cringe because it sounds too mythic: poking the dragon. Of course, the Sun isn't a dragon, but the image points to something real. There are moments when complex systems are more sensitive, moments when the system is already near a threshold and small inputs can change outcomes. So, did the sun respond? We can't prove it. We may never be able to prove it, unless future observations line up in a rare, data-rich way. But the question has been noticed, and that alone changes the conversation. Because once a community starts asking, what else might we be missing, it becomes harder to go back to only the simplest story. What other connections exist that we haven't thought to track? What other ways can the heliosphere surprise us, if timing matters as much as the pattern suggests? We may need to stop thinking of Earth as passive and start thinking of Earth as part of a larger system, a system where faraway motion can have nearby consequence. And that leads to the next question, the one that makes people uneasy. If space weather can influence Earth's crust at all, even slightly, what does the scientific literature actually say, and why is this topic so controversial? Part 7. Coronal holes and earthquakes, and the uncomfortable data. In science, there are questions that feel safe, and questions that can get you labeled as fringe. The question of whether solar activity affects earthquake timing often falls into that second category. Bring it up at a geology conference, and you may feel the temperature drop in the room. Most seismologists will tell you, correctly, earthquakes come from plate tectonics. Stress builds, rocks fail, and they might add, politely, that blaming the sky for what happens underground sounds unscientific. But here's the quiet complication: there is data. Not a lot, not decisive, but enough that dismissing the question entirely can feel premature. Every scientist learns a mantra: early correlation is not causation. Two variables can move together for reasons that have nothing to do with each other. Ice cream sales and drownings rise together. Not because ice cream causes drowning, but because both happen more in summer. Correlation without a mechanism is usually coincidence. But correlation with a plausible mechanism becomes evidence worth testing. And when similar patterns appear across different data sets, different methods, and different time spans, the question becomes harder to wave away. Studies on solar activity and earthquake timing go back decades. Many are published in smaller journals. Many are ignored by mainstream geophysics. A few are picked up by niche groups, creating small clusters of investigation interesting, but not widely integrated. Still, they exist, and some report results. For example, some analyses have found that certain categories of earthquakes appear slightly more common during periods of faster solar wind, with a delay of several days after a disturbance. Other work has looked specifically at high-speed streams associated with coronal holes and reported clustering patterns again. Not strong. Not universal, but intriguing enough to keep the question alive. There are also studies exploring ultra-low frequency electromagnetic signals and whether seismic events become a bit more likely when certain signal patterns appear. These findings, where they exist, are typically weak. That matters. We need to say it plainly. No one serious is claiming the sun flips a switch and causes earthquakes. The suggestion at most is a marginal influence, small probability shifts, small timing shifts, measured in days. But marginal effects can matter when the system is already close to failure. Faults don't wait forever. They move slowly toward a threshold, and the exact moment they cross it can depend on many small factors: tides, fluid pressure changes, nearby quakes, and possibly electromagnetic conditions. One proposed pathway involves Earth's global electric circuit. The ionosphere carries positive charge relative to the ground, and thunderstorms act like generators, maintaining that charge separation on a planetary scale. It's always running, always on, and solar wind can change ionospheric conductivity, which changes how currents flow in the upper atmosphere. During space weather disturbances, currents in near-Earth space and the upper atmosphere intensify, and some of that coupling can extend downward, producing induced currents in the ground currents that seek conductive pathways through rock and water. Here's where it becomes speculative. Fault zones are not simple cracks. They're fractured regions, often fluid-influenced, sometimes more conductive than surrounding rock. So in theory, induced currents passing through these zones could slightly affect conditions, for example, in fluid pressure or electrochemical state, which can, in turn, influence friction along fault surfaces. The effects would be tiny, and tiny effects are usually dismissed. But again, Systems near failure don't need huge pushes. They need precisely timed pushes. And if pulsing currents happen to match certain resonant tendencies in fluids or layers, amplification becomes possible, not large, not dramatic, but perhaps enough to shift timing. Most seismologists will object here, and fairly. They'll say the forces are too small compared to tectonic stress. And if space weather mattered strongly, we'd see obvious correlations every time. But we don't. Most geomagnetic storms pass with no major earthquake. That absence doesn't automatically disprove a relationship. It suggests any relationship would be conditional, only relevant when other factors align. And we already accept conditional timing influences in geology. Consider tides again. Tidal stress is tiny compared to tectonic stress, yet some studies show tidal cycles can influence timing when faults are critically stressed. The moon doesn't cause earthquakes, but it may nudge the clock in some situations. So the question becomes, if tidal forces can nudge timing under narrow conditions, why must electromagnetic forces be impossible? If the answer is because we haven't proven it, that's not a physics argument. That's a knowledge gap. And the knowledge gap exists for a reason. Earthquakes are deadly. Earthquake prediction has a long history of false claims. Every few years, someone announces a breakthrough electromagnetics, animals, groundwater chemistry, and it fails to deliver reliable forecasts. So the field has developed a strong immune response. Anything that resembles earthquake prediction, especially involving external cosmic triggers, often gets rejected quickly. That's understandable. It protects the public from false certainty, but it also carries a risk if a weak conditional relationship exists. Ignoring it could mean missing chances to refine how we assess risk. And that brings the story back to California. It sits on stressed faults. It has conductive geology in key regions. It has dense monitoring networks. And in late December 2024, in this narrative, it also sits beneath a magnetic configuration some consider vulnerable while high-speed solar wind approaches. If electromagnetic timing effects exist anywhere, they might be most visible there. And if they're visible at any time, they might be visible when the system is already restless. Not because the sun will cause an earthquake, but because if an earthquake happens anyway during or shortly after a strong solar wind arrival, the timing becomes hard to ignore. The question would shift from, is this idea ridiculous, to have we avoided looking closely for too long? The uncomfortable data doesn't say yes. It says maybe. Maybe weak correlations reflect a real mechanism, only active under specific conditions. Maybe we should watch carefully instead of dismissing the question because it makes us uneasy. And maybe, just maybe, the universe is about to run an experiment whether we're ready or not. Because the solar wind is coming, California is waiting, and one more factor is approaching. 2, a geometric configuration that some researchers watch. Not as astrology, but as physics. Part 8. The January 6th geometry. Planetary alignments can sound like horoscope language. So let's be clear, what follows is not mysticism. It's orbital mechanics. It's gravity. It's the same predictable motion that lets us forecast eclipses and navigate spacecraft across millions of kilometers. Planets move in patterns, and sometimes those patterns create configurations that are worth paying attention to. On January 6th, 2025, a rough alignment occurs. Earth, Venus, Jupiter, Saturn, and Neptune gathered broadly on the same side of the Sun. Not a perfect straight line, not a single-point conjunction, but close enough that, in some definitions, their combined gravitational influence on the Sun adds more than it cancels. This kind of geometry appears periodically, not once in 1,000 years, but not constantly either. And while gravity from planets does not push the Sun around in any obvious way, gravity does create tides even in plasma. Small, but not zero. And the Sun is not solid rock. It's layered, rotating plasma. Different latitudes rotate at different rates. That differential motion twists magnetic fields, stores energy, and eventually releases it in flares and eruptions. So even tiny tidal influences, especially from large planets like Jupiter and Saturn, become interesting in a non-linear system, not because they guarantee anything, but because they might slightly alter timing when the system is already near release. There's also the concept of the solar system's barycenter, the shared center of mass around which the Sun and planets orbit, a subtle dance point that shifts as the giant planets move. The barycenter is the solar system's shared center of mass, and it isn't fixed inside the sun's heart. It shifts, slowly, depending on where the planets are. When the giant planets gather more on one side, that center of mass can drift away from the sun's geometric center, sometimes even outside the sun itself, so the sun doesn't sit perfectly still. It makes a small, steady wobble orbiting around that moving point, pulled gently this way and that by distant mass. And that wobble may matter more than it sounds. Because wobble changes motion, it can subtly alter internal flow patterns, redistribute angular momentum, and shift how layers move against each other. Some researchers have proposed that this could influence when and how the sun's magnetic field reorganizes across a solar cycle. This idea remains controversial. Most solar physicists consider planetary gravity far too weak compared to the sun's own internal forces. But there's an awkward detail. Correlations keep showing up. In some datasets, solar cycle peaks appear more often when Jupiter and Saturn fall into certain repeating configurations. Other analyses suggest major eruptions sometimes cluster around particular geometric setups. None of this proves causation, and correlation alone isn't enough. But if correlations recur across time and methods, dismissing them completely creates its own question. Why do they keep appearing if there's nothing underneath? The January 6th alignment draws attention for one reason. It's not just one planet. Jupiter and Saturn do most of the tugging, but Neptune adds weight on the same broad side of the Sun, together. The barycenter displacement becomes more pronounced than any single planet would create, and the timing only about 2 weeks after the Goliath coronal opening became obvious, and near when the fast solar wind stream should be reaching Earth, creates a storyline that feels tightly spaced. Not by intention, not by design, just by physics, and by what can happen when influences stack on top of one another inside a complex system. There's also a historical echo people sometimes mention. In 1936, a somewhat similar configuration occurred. Jupiter, Saturn, Earth, and other planets gathered in a comparable geometry, while solar activity was elevated. That year included reports of stronger solar behavior, vivid auroras, and electromagnetic disturbances. Some have also pointed to an increase in seismic activity, though whether that was connected or simply normal variation is still debated. The sample sizes are small, the records are imperfect, no clean conclusion is possible. But the pattern, at least as a pattern exists, alignment, elevated solar activity, geomagnetic disruption, seismic events, it has appeared before, and, in this narrative, it may be lining up again. If there is a mechanism, some argue it could involve resonance, not bells ringing. Exactly, but resonance in the sense of timing. Small pushes, applied on a regular schedule, can build effects when they arrive at the right intervals. Planets provide a steady rhythm, their motion is predictable, and the sun's magnetic system has its own natural cycles and modes. If those modes line up even loosely with periodic forcing from planetary motion, you could, in theory, get modulation, not planets causing eruptions, but nudging the timing and intensity of eruptions that were already likely. A gentle influence, with potentially noticeable consequences. This kind of idea is uncomfortable for scientists trained to prioritize dominant forces. We're taught to ignore effects smaller than our error bars, to focus on what's biggest, clearest, most measurable, and to label the rest as noise. But complex systems don't always behave that way. Small effects can matter if they arrive at exactly the right moment in exactly the right rhythm. Weak periodic forces can matter when they match natural frequencies. And in a system as intertwined as the solar system with gravity, plasma flows, and magnetic fields interacting across distance, treating small as irrelevant, may hide the real organizing principle. Not always, but sometimes. So here we are in the story. January 6th approaches. The planets move into that geometry. The fast solar wind from the coronal opening presses on Earth's magnetic shield, and California, in this narrative, remains the region to watch. And if anything unusual happens, a large quake, satellite disruptions, grid disturbances, a question will rise immediately. Was it alignment? Was it timing? Or was it simply coincidence? The hard part is that we may not be able to answer cleanly, not because the answer is impossible, but because we don't have enough measurements. And we've spent a long time treating the question as fringe rather than testable. But even if January 6th passes quietly, even if nothing dramatic happens, that doesn't automatically mean timing is meaningless. It may only mean the system wasn't pushed at the exact wrong moment. Threshold systems can absorb pressure again and again, until suddenly they can't, and you rarely know which push will cross the line until after it happens. The only real preparation is understanding thresholds early, seeing the boundary before it fails. And in this telling, we're not there yet, not even close. But history leaves clues. And one of the most famous clues in space weather history may carry a shadow longer than most summaries admit. Let's talk about Carrington and why the largest solar storm in recorded history might not be as simple as we were taught. Part 9. The Carrington Shadow. September 1st and 2nd, 1859. The Carrington Event, the storm that overheated telegraph systems, sparked fires, and produced auroras visible far from the poles, even into the Caribbean. It's the example everyone cites, the benchmark, the worst-case story. And yet many retellings leave out something important because they focus on the flare, the coronal mass ejection, the raw magnitude. What they often skip is what came before, what Earth's magnetic environment was doing in the days leading up to it, and what else was happening in the system at the same time. When you look there, Carrington can start to resemble not just a huge UDAR, but a system already under strain, finally pushed too far. Richard Carrington was watching sunspots on September 1st, 1859, when he witnessed something extremely rare, a flare bright enough to be visible in white light. Most flares radiate in wavelengths our eyes can't see, but this one was intense enough to show itself directly, a brief, startling brightness on the solar surface. Within hours, auroras spread around the world. Telegraph systems behaved strangely. Operators reported sparks, equipment heating, even moments where lines carried current after batteries were disconnected, currents induced by the storm itself. For the most advanced technology of that era, it was a global failure. The standard explanation frames Carrington as a magnitude problem. A huge eruption, a fast CME, a direct hit. It reached Earth extraordinarily quickly, about 17 hours, rather than the more typical 2 to 4 days. And the resulting geomagnetic storm was extreme. If an event like that struck today, many estimates suggest severe consequences: transformer damage, satellite failures, widespread communication disruption, cascading impacts across interconnected systems. But even that isn't the whole story, because historical records point to something else. Earth's magnetic field appears to have been unsettled before the main blow arrived. Early magnetometer records, crude by today's standards, but meaningful, show elevated activity for days in advance. A compressed magnetosphere, higher than usual fluctuations, so the CME didn't slam into a perfectly calm shield. It hit a target already stressed. And then there's another eerie note in the historical accounts: reports of tremors and unusual ground rumbling in the weeks leading up to the storm. Were those connected with 19th century data? It's impossible to prove. But the timing raises the same question we've been circling. If geomagnetic disturbances can sometimes interact with Earth's crust even weakly, could a preconditioning phase exist? Not an earthquake maker, just a system nudger. And here's a detail that rarely appears in quick summaries: planetary geometry. In September 1859, Jupiter, Saturn, and Earth occupied a configuration that displaced the solar system barycenter away from the Sun's center. Not perfectly aligned, not a neat straight line, but a setup that could plausibly enhance those subtle wobble and tidal effects. The Sun, during solar cycle 10, was already active, already eruptive, already near reorganizations. The configuration didn't cause Carrington, but in this story, it may have nudged timing. And timing is everything if sequence is real. Our modern world is far more vulnerable than Carrington's world. We rely on satellites for navigation and communication. We rely on long transmission lines that span continents, lines that can behave like antennas for geomagnetically induced currents. When a severe storm drives currents into the ground, those currents can enter the grid and stress transformers. Transformers overheat. Transformers fail, and replacements aren't quick. They're specialized. They can take months, even longer. Enough failures at once can mean extended outages, not just a short blackout, but prolonged disruption. And because so many systems depend on electricity water treatment, Supply chains. Communications failures can cascade. This isn't meant as fear. It's simply the reality of interdependence. Many engineering studies have modeled these risks. They don't always agree on exact numbers, but their general conclusion tends to converge. Our resilience is thinner than we like to believe. But here's what those models often simplify. They treat Carrington like a single, massive hit. What they don't always model is Carrington as a sequence, a period of background disturbance, a preconditioned magnetosphere, possible crustal sensitivity, a geometry that may modulate solar timing, and then the main strike landing on a system already compromised. If you frame it that way, risk can look different, not because the sun produces Carrington-level eruptions every week, but because you're no longer waiting for one perfect outlier. You're watching for the right stack of conditions. Since 1859, we've had close calls and strong storms. 1,989, 2003, and in July 2012, a massive CME that might have been catastrophic had Earth been in its path. But it missed. We've had luck. And luck has a way of making preparation feel optional. People often argue Carrington-class events are rare once per century, or even less so. Why spend enormous sums protecting against something that probably won't occur soon? But if Carrington was partly a systems failure, a convergence of conditions, then the more relevant question becomes, how often do conditions align to make Earth maximally vulnerable? That might happen, more often than we think. And in this narrative, December 2024 begins to rhyme with September 1859, elevated geomagnetic background, unusual seismic signatures, a major solar structure aimed toward Earth, and an alignment approaching 50, pieces moving into position, a sequence forming. And if history is echoing, the next few weeks become a test not of fear but of whether we learned anything at all. But there's one more variable, a quiet piece of the Earth system that almost never enters space weather discussions because it seems too distant. Antarctica. The silent variable, Part 10. Antarctica isn't only ice. Beneath kilometers of frozen water lies a continent, mountains, volcanic regions, subglacial lakes, hidden valleys a landscape scientists still map using radar, gravity, and seismic surveys. And it is not inert. Heat rises from below. Some volcanoes exist beneath the ice. Subglacial water can flow, unseen, through darkness. And magnetic anomalies trace ancient rock structures across the continent. In late December 2024, within this story, something there appears to be shifting. Antarctica sits near the southern magnetic pole, though magnetic and geographic poles are not the same. The magnetic South Pole wanders, and its drift rate has, in recent years, required frequent model updates. In this telling, the pole's motion changes the geometry of field lines, altering how the polar region connects to the magnetosphere. Why does that matter? Because polar regions are special in space weather. They're where magnetic field lines guide particles downward more directly. That's why auroras cluster near the poles. Why high-latitude radio can be disrupted. Why the boundary between shielded and unshielded space is thinner there. And Antarctica is by nature under-monitored. It's remote. It's harsh. Sensor networks are sparse compared to the Arctic. In some ways, we're watching through fog. There are reports again. Within this narrative of unusual electromagnetic signatures, ultra-low frequency waves, whistlers, radio phenomena that can propagate through magnetic field lines and reflect between hemispheres. Some of these are normal processes, but the claim here is that their intensity and frequency increased. A few Antarctic magnetometers recorded disturbances that didn't look typical, and limited seismic monitoring hinted at signals that might align with increased subglacial volcanic activity. The data is sparse. Interpretations are uncertain, but it suggests something worth watching. Then comes a hypothesis, speculative, but built from physical ideas. Antarctica might act like an amplifier in certain conditions. Ice is electrically insulating. Sitting atop conductive rock and seawater, some describe this as a capacitor-like setup, an arrangement that could, in theory, store and release electrical stress under particular forcing. During geomagnetic storms, charged particles can precipitate into the upper atmosphere near the poles. Currents intensify in the ionosphere. Induced currents can form in the ground. In most places, those currents disperse. But the hypothesis suggests that in Antarctica, geometry and structure might allow unusual accumulation, possibly interacting with existing geological activity. And to be clear, this remains deeply speculative. Most geophysicists would argue subglacial volcanism is driven by mantle heat and tectonics, not space weather. And they may be right, but probably is not certain. And if any coupling exists, however weak, it deserves more monitoring than it currently gets. Because Antarctica doesn't stay in Antarctica, it influences sea level, ocean circulation, atmospheric patterns. The deep currents that help regulate climate begin in cold polar waters. The continent is remote, but not isolated. If Antarctic systems shift, the effects can propagate outward. There's also timing. December is Antarctic summer. The continent leans toward the sun. Solar illumination is high. The ionosphere can be more conductive. Coupling pathways can change with season. And on December 21st, 2024, the southern summer solstice arrives, the peak of that tilt. So if a strong solar wind stream arrives near that window, and solar illumination is at maximum, it adds one more coincidence to the stack. And in this story, the question becomes soft but persistent. How many coincidences can align before we admit we might be looking at a sequence, another alignment, another moment where influences add together, instead of fading out? And no, Antarctica won't transform overnight. Ice sheets don't fall apart in a single evening. If volcanic activity shifts, it may happen beneath kilometers of ice, hidden from ordinary view, noticed only through sparse seismometers, and tiny, slow changes in how the ice moves. But tiny changes don't stay tiny forever. They accumulate. They engage feedback loops. And in a climate system as intricate as Earth's, small nudges can sometimes begin large reorganizations. That's how ice ages begin and end, how circulation patterns flip, how the planet moves between stable modes, not always smoothly, but sometimes in sudden steps, after thresholds are crossed without warning. So add Antarctica to the list. Add it to the growing tally of unusual at the same time. Interstellar flyby, check. The Goliath coronal opening, check. A magnetic shield, trending weaker, check. Seismic oddities, check. An approaching alignment, check. And now, Antarctica, with reports of unexpected electromagnetic behavior and hints, however uncertain, of subsurface activity. Any one item could be noise. But when many independent signals stack together, noise starts to resemble information, a pattern, a shape, almost like the planet is responding not to one thing, but to a combination of influences our models rarely treat as connected, because nothing is truly isolated. Everything couples, eventually, and when multiple connections activate at once, systems can reorganize. Phase transitions can happen. The rules, or at least the behaviors we're used to, can shift. We may be entering unfamiliar territory, not because each individual event is unprecedented, but because the combination is. And combinations often matter more than linear predictions suggest. Earth isn't a simple machine with simple outputs. It's a complex, adaptive system full of thresholds, feedbacks, and emergent behavior. And we're about to learn whether those behaviors stay within familiar bounds, or whether the system is moving into a regime where new patterns appear, old ones fail, and prediction becomes difficult, not only because we lack data, but because the system is changing faster than our models can keep up. And there's another layer that complicates this even more, a shift that's only become unavoidable in the last few years. We're not just forecasting space weather with humans and physics models anymore. We're letting AI do it. And it's doing it surprisingly well. Part 11. AI is now forecasting space weather better than humans in many tasks. Machine learning has moved quickly into space weather prediction. Over the past few years, some models have shown accuracy that rivals and sometimes exceeds traditional approaches. In certain tests, they can anticipate flare likelihood hours ahead, with success rates that can climb high, sometimes above 8 out of 10, depending on the dataset and the definition of success. They can estimate geomagnetic storm strength with strong performance, sometimes matching or outperforming operational tools. They can detect subtle precursors in solar wind streams, patterns a human analyst might overlook. And here's the unsettling part: we don't always know how they're doing it. Not in a transparent, step-by-step, physical explanation. The model produces a forecast, and the forecast is often right, but the internal logic is opaque, a black box that works. That is both wonderful and a little frightening. Wonderful because better warning time protects things. Satellites can enter safer configurations. Grid operators can adjust loads. Astronauts can take shelter in more shielded areas. Fewer surprises. Less damage. That's a clear win. But it's also unsettling because we are outsourcing understanding to systems that can't explain themselves. We begin to trust a prediction without fully knowing the reason it's accurate. And in a domain as non-linear and surprising as space weather, trust without comprehension can become fragile. The reason machine learning can succeed here is simple. Neural networks are extraordinary pattern detectors. You give them vast archives, solar imagery, wind parameters. Out comes thousands of examples where you know what happened next, and they learn associations, not mechanisms, not why. Just when these conditions appear, that outcome often follows. If the pattern holds enough of the time, prediction becomes possible, even without physics. Traditional forecasting takes a different path. Physics-based models attempt to simulate the solar wind traveling from the sun to Earth, then estimate how the magnetosphere will respond. They model coupling with the ionosphere. They use equations tied to known physical laws. They're interpretable. You can trace the reasoning, see where uncertainty enters, and understand which processes matter. But they're also slow and imperfect. They can require enormous computation, and they can be wrong because the system is chaotic, sensitive, and partly unmeasured. So we end up with a trade-off. Physics gives you understanding, sometimes at the cost of accuracy. AI can give you accuracy at the cost of explainability. For day-to-day operations, accuracy often wins. That's why many centers now run machine learning models alongside traditional ones. In some cases, AI tools are becoming primary signals, with physics-based models used as cross-checks. It's happening quietly, because it works. But researchers still feel uneasy, because what happens when the AI predicts something truly unfamiliar? What if the model suggests an extreme storm and the physics-based tools don't show a clear pathway? Do you issue the warning? Do you trust the black box? Or do you hesitate and risk missing the one moment when hesitation mattered most? And there's another problem: failure modes. Machine learning is strongest when tomorrow resembles yesterday. It performs well when the future sits inside the envelope of past examples. But space weather can do new things. Solar eruptions can appear in forms we haven't seen in the training data. And the sun itself evolves, its cycles are not perfectly repeating. Solar Cycle 25 has already surprised forecasters in its intensity. If something genuinely novel occurs, an AI model might fail. Or worse, it might fail confidently. It could offer reassurance precisely when conditions are outside its learned world. Some groups attempt to solution hybrid models. Physics plus AI using physical constraints to keep the learning grounded, to reduce the chance the model latches onto spurious correlations. But hybrids are difficult. Sometimes they become less interpretable than physics alone, and less accurate than pure AI. The perfect middle may exist, but it hasn't clearly arrived yet. So what does this mean for the Goliath coronal opening? It means some of the arrival time forecasts and storm intensity predictions you hear may be produced, at least in part, by systems that cannot fully explain their inner logic. They're built on decades of patterns. They are statistically reasonable, but they are not guarantees. And if December 2024 is a truly uncommon configuration, a sequence not well represented in the satellite era, then even strong models may be extrapolating into unfamiliar territory. We won't know until afterward whether the predictions were correct. And by then, it won't matter whether they were right for the right reason or right by coincidence. There's a wider idea here. We're entering a time when prediction can outrun understanding, when we can forecast outcomes without being able to explain them. That helps with immediate decisions, but it's weaker for long-term resilience. Understanding lets you adapt. It helps you recognize when the world has shifted outside the past. Prediction without understanding can be brittle. It works until it doesn't, and when it breaks, you may discover you never built the conceptual tools needed to reason through a novel situation yourself. Space weather is only one example. Climate, earthquakes, markets, medicine. Many domains are moving the same way, and every domain faces the same tension: accuracy versus transparency, speed versus comprehension, Trust in algorithms versus trust in human judgment. There's no perfect answer. Both approaches have value, but the direction is clear: we are delegating more decisions to systems we don't fully grasp. And the delegation accelerates with every success story, every moment where the machine beats the human, and we simply say, well, it works. The question for space weather is whether that shift happens fast enough to protect us from the rarest events. Can AI recognize the warning signs of once-in-a-century storms from only a few decades of training data? The hope is yes. The worry is that we're asking it to predict something it has never truly seen based on patterns learned from conditions that may not apply anymore. If that worry is valid, then forecasts could be less reliable exactly when we need them most. Right when the shield is thinner and the sun is pressing harder and multiple variables are stacking. One model says it should be manageable, another suggests it could be worse, and everyone hedges, because nobody wants to be the one who overreacted or the one who missed the warning. So we watch, we wait, and we hope the tools, whichever ones we trust, are right, because there's another variable changing too deep within Earth itself, a slow shift, confirmed recently in new research, that may matter for the magnetic field in ways we're only beginning to map. Earth's core appears to be slowing its relative rotation. Part 12. Far beneath you, about 5,000 kilometers down, is Earth's inner core, a solid sphere of iron, roughly moon-sized. It doesn't rotate in perfect lockstep with the surface. Seismic waves have suggested for decades that it can spin slightly differently than the mantle and crust above. But newer seismic analyses reported in major journals have strengthened a surprising conclusion: the inner core's rotation relative to the surface has been decreasing, not just different, but slowing, compared to what it appeared to be doing before. And scientists are still debating what that implies for the magnetic field, for the magnetosphere, and for how resilient our shielding will be during active space weather. To understand why it matters, we have to zoom out. Earth's magnetic field is generated in the outer core, a thick layer of liquid iron extending from about 3,000 to 5,000 kilometers deep. That liquid metal is hot, conductive, and in motion, churning due to heat flow and convection as the planet slowly cools. Moving conductive fluid creates electric currents. Those currents create magnetic fields. This is the geodynamo, the engine that has maintained a protective field for billions of years. The inner core doesn't directly generate the field, but it influences the system. The inner core grows slowly as the planet cools iron, crystallizing out of the liquid. That process releases heat and changes composition, helping drive convection in the liquid outer core. The inner core can also anchor or shape flow patterns above it, guiding how the liquid organizes itself over time. So if the inner core's rotation changes, those flow patterns can shift. And if the flows shift, the magnetic field generation can shift too. It's a coupled system: motion influencing field, field influencing motion, everything interacting. The studies behind this use seismic waves from earthquakes, tracking subtle differences in travel times through Earth over many years. It's painstaking work, decades of data, many events, careful statistics, but the overall result has been interpreted as clear. The relative rotation rate appears to have decreased for at least the last decade, possibly longer. Some interpretations suggest the earlier superrotation may have slowed dramatically, perhaps even approaching a near match with the mantle, or, by some readings, slightly slower. Why is this happening? The simple truth is we don't fully know. One idea involves gravitational and electromagnetic coupling. The inner core experiences forces linked to the magnetic field in the outer core, and gravitational tugs from uneven density in the mantle above. Those influences can apply drag over time. Another possibility is that this is part of a longer oscillation, a cycle of speeding up and slowing down across decades or centuries. Or it could reflect a deeper shift in internal dynamics. The data tells us the what, the why is still in motion. And here's why it matters to the magnetosphere. If inner core behavior affects outer core flows, and outer core flows generate the magnetic field, then shifts in the deep interior could connect, indirectly, to field strength. We already know the field has been trending weaker over the last couple of centuries, with notable regional lows such as the South Atlantic anomaly. Could core changes be related? Possibly. Perhaps. But it's not a neat one-to-one timeline. The magnetic weakening trend extends farther back than the most recent measurements of slowing. So this isn't a simple switch. It may be that both are symptoms of deeper processes within the core system. If weakening continues, the magnetosphere can shrink, thin zones can broaden, vulnerability increases. Not overnight, not as a sudden collapse, but as gradual risk accumulation. And the problem with gradual change is this slow degradation can still cross a threshold quickly. Systems can fail fast after weakening slowly. And when people hear weakening field, another fear appears: reversal. Geomagnetic reversals have happened many times in Earth's history. The rock record shows them clearly. On very long averages, they occur every few 100,000 years, but the timing is irregular. The last full reversal was about 780,000 years ago. Statistically, you can say we're due, but due does not mean about to happen. Reversals can involve long periods of instability, multiple poles, wandering structure, partial recoveries over thousands of years. And right now, in this story, we are not in a reversal. We're in a period of change, and we're still learning what that change truly implies. The magnetic field is weakening, but it's still a dipole. It still protects us. Yet the direction of change is unsettling, and the idea of the inner core slowing adds another layer of uncertainty because it hints the geodynamo may be shifting in ways we don't yet understand. If the core is slowing, what else is changing with it? Are there flow patterns in the liquid outer core we simply can't see because we don't have instruments that can reach that depth? Are there feedback loops we aren't modeling because we don't even know they're there? The core is inaccessible. We can't drill to it. We can't place sensors inside it. We infer its behavior indirectly from seismic waves and from magnetic measurements at the surface. It's like trying to diagnose an engine by listening to the sound of exhaust from far away. You can learn something, but you miss details, and sometimes the details are everything. So here's the uncomfortable synthesis. Earth's deep interior appears to be shifting. The magnetic field is trending weaker. The magnetosphere may be more vulnerable than in recent history. And during this window, we're facing an unusually sustained solar wind stream from a massive coronal opening that appeared at a suspiciously tight moment in the sequence. Coincidence? Possibly. Pattern? Also possible. And if it's pattern, if there are links between internal dynamics and space weather vulnerability we haven't recognized, then those links become essential for risk assessment in the coming decades. Because if Earth is moving into a prolonged period of magnetic weakness, whether or not it leads to a reversal, then every solar storm matters more. Every coronal hole matters more. Every space weather event becomes a sharper test. A test of whether our civilization can function in an environment that is slowly becoming less forgiving. But step back, further back, because there's another perspective, one that has only become clearer in recent years with new kinds of astronomical observation. A perspective that says the universe may be far more magnetic than we assumed. And if that's true, it changes the context of everything. Part 13. James Webb and a magnetized universe. When you look at space images, you see light, stars shining, nebulae glowing, galaxies spiraling into luminous arcs. But light is only part of the story. Behind what we see is an invisible framework, magnetic fields threading through gas and dust, guiding matter, channeling energy, shaping structure in ways that become obvious only when instruments are sensitive enough to reveal the pattern. James Webb has expanded what we can observe, and some interpretations of its observations have pushed astronomers to rethink how magnetism behaves, from star-forming regions to galaxy-scale structures. In stellar nurseries, magnetic organization can appear strong and surprisingly coherent. Around young stars, protoplanetary disks show structures that may be influenced by magnetic behavior, possibly shaping how and where planets assemble. On even larger scales, galaxies exhibit magnetic fields spanning vast distances, fields that, in some observations, look more coherent than older models predicted. Wherever Webb looks, magnetism seems to be doing more than many people expected. None of this means magnetism is a new discovery. Astronomers have known for decades that magnetic fields matter. They influence star formation by adding pressure against collapse. They accelerate particles in extreme environments. They shape stellar winds. They govern the sun's corona. But the prevailing intuition has often been gravity as the main architect, and magnetism is a modifier. Some of what we're seeing now encourages a different question. What if magnetism isn't secondary in the way we assumed? What if in many contexts. Magnetic organization is a fundamental scaffold working alongside gravity to shape the universe. And here's why that matters for Earth and for what we're discussing in December 2024. It reframes where we sit. Earth's magnetosphere isn't an isolated bubble. It's part of the heliosphere. The heliosphere sits inside the local interstellar medium. That medium is embedded in the Milky Way's magnetic structure. And that, in turn, exists inside wider intergalactic magnetism. Nested fields, all the way up. Each scale can influence scales above and below it. Not always strongly, not always measurably, but influence is possible. Solar physics often treats the sun as self-contained, its dynamo driven by internal flows. Its cycles emerging from its own plasma dynamics. Why invoke the galaxy at all? But if magnetic fields are strong enough to organize galactic-scale structures, then it becomes harder to dismiss the idea that they might also influence heliospheres, their shape, their shielding efficiency, their responsiveness to disturbance. These remain fringe ideas in many circles, not because they're automatically impossible, but because they are notoriously hard to test. Still, Webb's broader picture makes them harder to ignore. There's also a nearer connection: cosmic rays. High-energy particles from distant events in the galaxy constantly pass through the solar neighborhood. The heliosphere deflects many, but not all. Cosmic ray intensity varies with the solar cycle, because the solar wind's magnetic structure changes the shielding. But cosmic rays can also vary with the sun's position and environment in the galaxy, with the local interstellar magnetic field, and with regions of higher or lower particle flux. When cosmic rays interact with Earth's atmosphere, they create cascades of secondary particles, touching atmospheric chemistry, cloud processes, and more topics still debated in detail, but studied seriously. So you can ask carefully, could changes in the broader magnetic environment modulate the sun? Could they alter cosmic ray shielding? Could they, through chains we haven't mapped, influence space weather timing? It sounds like a stretch, and it may be small, but small effects can accumulate, and in systems with thresholds. Small effects timed correctly can trigger reorganizations that look much larger than their cause. If Earth is responding to multiple influences at once, then ignoring any influence because it seems minor could mean missing the tipping point. Webb has also helped expand the study of magnetospheres beyond our solar system. Some exoplanets, especially close-in gas giants, appear to endure extreme stellar winds and still maintain magnetic shielding. Their magnetospheres compress, but persist. They interact with their star's field in dramatic ways, producing auroral and radio signatures detectable over vast distances. These worlds become laboratories, showing how magnetic systems behave under pressure. And what those systems suggest is this: under stress, magnetospheres can behave non-linearly. They don't always degrade smoothly. They can reorganize suddenly. And sometimes that reorganization produces phenomena that don't appear under ordinary conditions. Applying this to Earth is speculative. We are not being pushed like a hot Jupiter. But every weakening of the field, every thinning of the shield, every rise in solar wind intensity moves us along a spectrum toward regimes where nonlinear behavior could matter more. Webb doesn't tell us when that boundary is crossed, but it hints that such boundaries exist. And if December 2024 marks the start of a period where Earth's magnetosphere is tested more severely than recent decades, then those distant examples stop being purely academic. They become reminders of what's possible. The universe is magnetic, perhaps more magnetic than we thought. And that means Earth inside its magnetic bubble, inside the sun's heliospheric field moving through wider magnetic architecture, may be subject to influences we haven't fully accounted for. Does that change NOAA's immediate forecast? Not directly, but it changes the context. It changes what we may want to monitor, and it changes how we interpret subtle anomalies that don't fit neatly inside Earth is isolated. Because Earth isn't isolated, we're connected. And connections matter, especially now when our technological civilization is more interdependent and more vulnerable than ever. Which brings us to satellites, to the infrastructure above our heads, and what happens when it begins to fail quietly. Part 14. The quiet crisis in space infrastructure. There are thousands of active satellites orbiting Earth communications, navigation, weather, imaging, military systems, a web of machines providing services modern life barely notices anymore. GPS guides navigation. Weather satellites support forecasts. Financial systems rely on timing and links. Communications lean on space relays. 60 years ago, most of this didn't exist. Now, we are deeply dependent. And the uncomfortable truth is, satellite systems experience anomalies more often than most people realize. Not sudden collapse, not dramatic headlines, but incremental issues, resets, glitches, radiation upsets, small fault patterns that suggest the environment is challenging, and our adaptation may not be keeping pace. Operators rarely advertise failures. It's bad for confidence and business. So much of what we know comes indirectly: industry summaries, academic studies of disclosed anomaly data, insurance reporting, and occasional whistle-level concern from people inside the system. And one signal that appears repeatedly is anomalies tend to rise around space weather disturbances, not always, not uniformly, but enough to be statistically noticeable in some analyses. Satellites fail for many reasons: hardware fatigue, software errors, debris impacts, radiation damage. But space weather produces specific stressors. Solar activity can swell Earth's upper atmosphere, increasing drag in low orbit and altering trajectories. Charged particles can accumulate on surfaces, building voltage differences that discharge suddenly, stressing electronics. Geomagnetic storms can compress shielding regions, increasing radiation exposure, and flares can ionize the upper atmosphere, creating density surges that make orbit prediction harder. Engineers know these risks. Designs include shielding and procedures, safe modes, storm protocols. But those designs rely on historical data on what the satellite era has experienced as worst cases, plus some margin. If conditions drift beyond historical norms, then anomaly rates rise above design expectations. And some operators quietly suggest we may already be leaning that way because solar cycle 25 has been more active than predicted. Insurance markets often detect this before the public does. Underwriters track risk. They watch failure rates. They adjust premiums. And in recent years, the space insurance market has reportedly tightened, asking harder questions, demanding more detailed risk assessments, sometimes limiting exposure for failures linked to space weather. That is a market signal, money reacting to probability. There's also a risk that doesn't fit neatly into storms and flares cascading failures. Earth's orbital environment is crowded. Low Earth orbit is packed with satellites and debris. Millions of fragments move at extreme speeds. Any collision can be catastrophic. Space weather can change debris behavior. Atmospheric expansion increases drag, helping some debris decay faster over time, which sounds helpful, but the effect is uneven. And storms can also reshuffle orbital pathways in the short term, creating temporary windows where collision probabilities rise. If a collision happens during such a window, it can create more debris, raising the risk for others. That's the feared cascade scenario often discussed in orbital debris studies, a chain reaction where collisions breed collisions until certain orbital bands become extremely difficult to use. We are not there. But the trend is not comforting. Anti-satellite tests have created debris fields. Mega constellations add enormous object counts, and variable atmospheric conditions make tracking and prediction harder. The quiet crisis is this: dependence is rising at the same time risk is rising. Autonomous systems rely on navigation signals. Internet delivery increasingly leans on satellite networks. Military operations depend on recon and links. Climate science depends on continuous observation. If we lose enough satellites at once by storms, collisions, or cascades, recovery is not quick. Building and launching replacements can take years. Could the Goliath coronal hole do this directly? Probably not in a single blow. A coronal hole stream is different from a CME. It's often gentler but longer, and sustained pressure has its own danger. It drains resilience. A brief storm is easier to ride out. A multi-day disturbance keeps systems stressed and reduces clear recovery windows. In a prolonged event, operators face continuous management, more anomalies, more decisions, more fatigue. And fatigue is where mistakes happen, not because the system exceeded design limits, but because humans and automation can misread conditions and choose imperfect responses. The industry is aware. Committees exist. Standards evolve. Debris mitigation improves slowly. But the pace of change in space activity and the growth of dependence may be outpacing the speed of preparedness. We are building faster than we are understanding. And that sets the stage for surprise failures that seem inexplicable. Cascades nobody predicted. Systemic risk unfolding not from one break, but from many small breaks aligning. That's what systemic risk looks like, a web of dependencies where small failures amplify each other until the whole system reorganizes into a new state, often a worse one. So if December 2024 is the beginning of a sharper testing period, we're about to learn something fundamental. Are our systems resilient or brittle? Did our models capture the real risks or miss the shape of the problem? Which brings us to the final question, the big synthesis. Are we watching a reformat? Is Earth from core to magnetosphere to surface, moving through a transition? And if so, what does that mean for the next months, years, decades? Part 15. Are we watching a reformat? Here's the thread we've followed. An interstellar visitor passes through the solar system, moving through plasma and magnetic structure. Seismic anomalies appear. A massive coronal opening forms on the Sun, a line toward Earth. Solar wind streams toward a planet whose magnetic field has been weakening for centuries, and whose deep interior shows new signs of change. Resonance patterns appear during conditions when they shouldn't. An alignment approaches. California shows overlapping electromagnetic and seismic signals. Antarctica hints at unusual behavior. Satellite anomaly rates quietly rise. AI forecasts improve, but can't fully explain themselves. And all of that leads to a single, quiet question. And the universe, according to our newest instruments, looks more magnetic and more interconnected than we once assumed. Each piece we've talked about has some form of evidence. Each piece has observations behind it. The question is not whether the pieces exist. The question is whether they belong to the same story. The conventional answer is simple no. These are separate phenomena, coincidences, patterns that feel meaningful only because the human mind is built to connect dots. In that view, the Sun doesn't respond to passing bodies. Earthquakes aren't driven by space weather. Planetary geometry doesn't matter. Core dynamics evolve too slowly to shape what happens in any given month. And satellite anomalies are just the cost of operating delicate technology in a harsh environment. Everything has an ordinary explanation. Nothing requires exotic mechanisms. Nothing requires a grand systemic shift. It's the safest position, and it might be correct. But might isn't certainty. And there's another interpretation, one that takes interconnections seriously. One that asks what changes when you stop treating Earth as isolated subsystems and start treating it as a single complex system, where feedback loops and thresholds link distant processes. In that view, sequence matters. Timing matters. The combination of pressures can matter more than any individual pressure. What we're seeing might not be separate events, but symptoms, a system under strain reacting to multiple influences at once, moving closer to a threshold where it shifts from one stable mode to another. That is not a prediction of apocalypse. It's not a claim that the world is ending. Systems reorganize without destroying themselves. They transition. They adapt. They settle into new equilibria. But transitions are disruptive. They produce behaviors that don't appear during calm stability. And if Earth is in a transition, if weakening magnetic shielding, unusual solar behavior, seismic stress, and a particular cosmic geometry are stacking together, then the next few months could bring events our models don't anticipate. Not because our models are useless, but because they're tuned to normal conditions. And these may not be normal conditions. The reformat metaphor comes from computing. When you reformat a drive, you aren't destroying the machine. You're reorganizing it, clearing old structures, creating new ones. From the perspective of the old data, it looks like loss, but it's actually preparation for a different configuration. Earth doesn't reformat like a computer, but Earth does reorganize. A geomagnetic reversal is a reorganization. An ice age is a reorganization. A mass extinction is a reorganization. An old balance collapses. A new one emerges. And the transition period between them can be chaotic, difficult to predict, filled with anomalies that stop looking like anomalies once you realize they're the signature of change. So, are we inside a phase change? That's the question. And the uncomfortable part is that we rarely know in real time. Phase changes don't announce themselves clearly while they're happening. They look like noise, like variability, like a system behaving erratically. Only afterward, when you map the data, does the shape of the transition become obvious. Historians of climate see this pattern again and again: a stable era, an era of rising variability, a sudden shift, then a new stable state. The variability phase can last years, sometimes decades, and people living inside it mostly experience it as strange weather, surprising events, a world that feels less predictable. They don't always recognize a transition until the new normal finally settles. If Earth's magnetic field is moving toward a reversal, we would be in that variability phase. The field drifts. Regional weak spots expand. The South Atlantic anomaly grows. Deep dynamics shift. Those are documented observations, not fantasy, not disputed in the basic sense. What remains uncertain is speed and secondary effects. A weaker field can allow more solar energy to couple into the near-Earth environment. More coupling can mean more ionospheric disturbance. More disturbance can mean more pathways for currents. More pathways can increase the chance of interactions with stress systems, fault zones, volcanic regions, polar environments. Each link is modest. Each step is subtle. But long chains don't require one strong link if enough weak links align at the same time. And it may not be only Earth. The solar system itself moves through the galaxy, through regions with different particle environments, different cosmic ray flux, and potentially different magnetic conditions outside the heliosphere. The Sun is not sitting in one unchanging external sea. We drift, we travel, and conditions beyond the heliosphere can change. Those changes might influence how the heliosphere shapes itself, how it shields, how it interacts with the interstellar medium, and how effectively it buffers the inner solar system. This is speculative. It sits near the edge of what we can measure cleanly. But the possibility exists that solar cycles are not purely internal clockwork, that they may be modulated slightly by external context. If that's true, treating the Sun as fully isolated means we miss part of the driver. So where does that leave us? It leaves us doing the only honest thing: watching, measuring, collecting evidence. The solar wind from the coronal opening will arrive. The geomagnetic storm will be mild, or it won't. Satellites will hold, or some will glitch. California's faults will stay quiet, or shift. January 6th will pass with nothing notable, or with something that makes people look twice. And afterward, we'll analyze, revise models, update assumptions. That's how science works. But there's always a small possibility, non-zero, that we learn something uncomfortable, that our models missed a connection, that what we dismissed as implausible held a thread of truth, that the system responded in ways we didn't expect because we were studying pieces instead of the whole. Earth's shield is not gone, not shattered, not absent, but it may be thinner. And thin shields don't always fail by breaking cleanly. They fail by leaking, by uneven, weak zones, by accumulated stress rather than one dramatic blow. The Sun presses, the core shifts, and the wider universe looks more connected than we once assumed. Meanwhile, we stand on a planet that has been adapting for 4.5 billion years, enduring tantrums from its star, reshaping itself through internal and external forces, finding balance again and again. We have been fortunate to live through a relatively stable phase, a period where shielding felt reliable, where storms were mostly manageable, where technology worked often enough to feel permanent, where civilization grew confident, sometimes complacent, in the idea that stability is the default. But stability is never the default. It's a phase, and phases end. Sometimes slowly, sometimes quickly, sometimes with warning signs we only understand in hindsight. So, the final question becomes, are we defending against the future, using the rules of the past? Because if the answer is yes, then we're about to learn whether those rules still hold, whether models still apply, whether our preparations were truly enough, or whether the universe is ready to behave in a way we haven't prepared for. Not to punish, not to threaten, simply because it can. We are not in control. We are observers and participants living on a dynamic planet, inside a dynamic solar system, inside a magnetic universe that doesn't require our understanding to keep moving. It simply is. And it will keep doing what it does. The solar wind is coming. Earth is waiting. And somewhere, deep below 5,000 kilometers down a sphere of iron, turns a little differently than it used to, maintaining a field that is thinner than it once was, holding a shield that may be strained, at an awkward moment. So we watch. That's what we can do. Watch, measure, and hope the patterns are only noise, only coincidence, only the universe rolling dice. But if there is signal in that noise, if timing matters as much as some data hints, then December 2024 might later be remembered as the moment everything shifted. Or it might be remembered as nothing at all, just another month in a long chain of months where life continued exactly as it always has. We'll know soon. The geometry is nearly complete. The solar wind is in transit, and Earth vulnerable, resonant, and quietly enduring is about to learn whether its weakened shield can hold, or whether this is the moment we discover what happens when protection slips. And the universe reminds us how delicate our small blue world can be.